Let's discuss dynamics of rotation. Welcome again to Engineering Physics. Dynamics for rotational motion is completely analogous to linear or translational dynamics. Dynamics is concerned with force and mass and their effects on motion. If you have ever spun a bike wheel or push a merry-go-round, you know that force is needed to change angular velocity. In fact, your intuition is reliable in predicting many of the factors that are involved. For example, we know that a door opens slowly if we push too close to its hinges. And furthermore, we know that the more massive the door is, the slower it opens. The first example implies that the farther the force is applied from the pivot, the greater the angular velocity and acceleration. Another implication is that angular acceleration is inversely proportional to mass. These relationships should seem very similar to the familiar relationships among force, mass, and acceleration embodied in Newton's second law of motion. There are, in fact, precise rotational analogs to both force and mass. Take another example of a worker using to rotate a gear with a wrench. He would apply force at the outermost part of the wrench instead of the closest for some reason. So, why not the middle portion, or the closest part of the handle to the grip? Torque is a rotating force about an axis. In advanced programs, you would hear about this as twist or torsional force, but most often, this is commonly called moment, designated as m. The formula for torque is given as tau is equal to F times L, where tau is torque, F as the force, and L as the lever or moment arm. To illustrate, suppose we have a force at a certain position from some point A. Torque can be solved as the magnitude of the force multiplied by the perpendicular distance of the force from the point. So, why perpendicular? It is because lever arm is the closest distance of the force to the axis. Like the other parameters of rotational motion, positive torque considers counterclockwise motion because it follows the progression of the quadrants from quadrant 1 to 2, then 3, and finally 4. How do we solve for torque? In this example, two situations are presented. What is the torque generated by the forces to the point? The first image shows a force of 10 newtons moving at a certain direction but has a perpendicular distance of 2 meters from the axis point A. So torque can be computed as force times moment arm, which would turn out as tau is equal to 10 newtons times 2 meters, giving us 20 newton meters. From the other situation, the force of 10 newtons is applied 12 meters away from the axis. But if we draw the line of force, it penetrates the axis, so we cannot arrive at a perpendicular distance, making the lever arm 0 and also our torque as 0. From the earlier part of the course, we discussed that static equilibrium is attained when the summation of forces is 0. So let's add another important parameter to that concept, stating that summation of moments is also equal to 0. So in two-dimensional analysis, we can use summation of horizontal forces, summation of vertical forces, and summation of moments equal to 0. And for 3D, we can use all of these 6 equilibrium equations. Here is a classic example for seesaw balance. From the illustration, how far from the fulcrum should a smaller child sit to balance the seesaw? To keep static equilibrium, we can use the formula of the summation of moments is equal to 0. With two forces present, one from the smaller child is counterclockwise and the force from the bigger child is clockwise. So the formula can be expanded as FL counterclockwise less FL clockwise is equal to 0. So if we plug the values, we get 500 newtons times x less 1000 newtons times 1 meter, which becomes 500x is equal to 1000, and the answer would show that x is equal to 2 meters. That would be the distance of the smaller child from the fulcrum. Another example is the following. The given plate is fixed at point A and is allowed to rotate at this point. Find the total torque applied by the forces. With the requirement of the total torque, we can start by saying that total torque is equal to m1 plus m2 plus m3, as we have three forces. While we expand, we can also consider the rotation altogether. So checking on force 1, which rotates in counterclockwise, we can say that it is positive FL. The second force F2 moves clockwise, so it will be negative FL. The third force can be denoted as a force through the point, so this will give a zero lever arm, making its FL value as 0. So let's place the values. The total moment is equal to F1 of 4 kilonewtons with its lever arm of 2 meters, less force 2 of 5 kilonewtons multiplied by its lever arm as 4 meters, which generates the answer negative 12 kilonewton meter, which means that the moment is rotating clockwise. The next case states, if the fixed point was instead at point B, determine the corresponding torque change. And still working with a total moment of m is equal to m1 plus m2 plus m3, we can expand with the signs where f1 in this case will be rotating clockwise, making the formula negative FL. Force 2 will be moving through point B, making its moment 0, and force 3 has a similar case. So the moment can be computed as negative 4 kilonewtons by 2 meters, or that is negative 8 kilonewton meter. The third case keeps point A as the reference point, but force 2 is applied at point B instead of point C. With the total moment to be solved, being m1 plus m2 plus m3, we can check that F1 is still counterclockwise, making it positive just the same. F2 will be analyzed using the line of force, which should show that it would be acting similar to case 1 earlier. And force 3 passes through which would still be 0. So the formula will be computed similarly. That would be FL1 less FL2, or 4 times 2 less 5 times 4, which would still give us the same answer as negative 12 kilonewton meter, and this would still be clockwise. Center of gravity is identified as the point where weight is evenly distributed, balancing the whole system. They said that a person's center of gravity is considered to be at his belly button, but additional load to the person can also deviate the location of the CG or the COG. Center of gravity is often used with an individual system or with regular shapes. So taking these two geometric shapes, we can get the COG for the rectangle at its midpoint, and the triangle COG can be taken from the intersection of lines coming from the vertices bisecting the opposite sides. For example, what is the produced torque of a plank of wood with length of 3 meters and mass of 10 kilograms about a fulcrum as shown? So by illustrating, the problem of 3-meter plank of wood is allowed to rotate about a fulcrum. To solve for its torque, we should consider some kind of force with its lever arm. In this case, force is taken as the weight of the wood plank, which is 10 kilograms by 9.8 meters per second squared, and the lever arm will be from the fulcrum to halfway the plank, or 1.5 meters. So the answer is 147 Newton meter. Moment of inertia is a very important parameter in our design subjects. Also called rotational inertia, it would show the material's resistance to rotation. For a particle, the formula is I is equal to mr squared, but considering a system, moment of inertia will be computed as the summation of the moment of inertia of each individual part. The first type of moment of inertia is area moment of inertia, and this type is applied more in two-dimensional plane shapes. The formula with respect to different components are I sub x, which is the summation of bar sub I of x plus AR of y, and I sub y is equal to the summation of bar I sub y plus AR of x. The second type of moment of inertia is mass moment of inertia, which is used in solid materials. Also notice that the only difference between the two sets of formulas is the change from area, that, into mass. Check out the third part of Module 6, Elasticity.